Welcome to Calculus. This is Unit 3, the question quiz 2 stuff, which is implicit differentiation, inverse function, and inverse trig derivatives. We're probably going to do the first two today, and we'll have another video for this stuff later. I also am asking a question of what was the best movie musical of all time. So far, no one's guessed. Go ahead and put your guesses in chat for this video later. But I don't know if you're going to get it. Yeah, it's a real movie. It's not like something that was only in art houses or something. Let's begin. That was a warm-up if you want to do it at home. But I'm skipping it. So let's talk about implicit equations first. But before I do that, I really got to talk about explicit equations. And explicit equations, it doesn't mean bad words in them. Sometimes there are, like function. Or optimization. But these mean their equations in the y equals form. And that's what you're used to. Y equals x squared. Y equals. We explicitly say that express y in terms of s. So x. We're saying y equals this. We're being very clear. Now, the opposite of that, you still haven't guessed correctly in Zoom chat. Sorry. The opposite of that would be implicit equations. So it's where the y, there's an implied relationship between x and y, and there's an implied like y equals something, but it's not explicitly stated, but it's implied in there. That's where we get implicit. So basically, it's not in the y equals form. X squared plus y squared equals 1. X like this, x times y squared. Maybe you have multiple y's. You don't have an isolated y. Maybe it's a y to a certain power. So like even y squared equals x squared plus 1 would be implicit. Because that's x, y squared. Now, this is implicit form, too. But you might say, hey, I could just divide by x on both sides, and I could get 1 over x. So sometimes you can rearrange it to an explicit form. But, and technically, this actually, and technically, these aren't the same equation right here, because the domain, in this case, x can't equal 0, but in this case, x can equal 0. Wait, no, it can't either, because that would never be true. I don't know. Maybe they are the same. Yeah, because I guess it's implied anyways. But so sometimes you can arrange, but there's certain cases where you can't. So for example, like I took this equation, you say, oh, just square root both sides. So you get y equals the square root of x squared plus 1. No, you can't do it because it's technically plus or minus. So really, square rooting this would turn into 2 y equals equations. So it kind of works where you isolate it, but it's 2 explicit equations. That doesn't really work. And a case like this, you could not isolate the y at all. Like, there's no way to isolate it when it's in terms. So sometimes you can't isolate the y. So that's what I mean by implicit equations. All right? All right, so sometimes in these equations, what are you going to have to do in calculus? That's your real question, right? What you're going to have to do is you're going to usually have to solve for dy dx because you have to derive at some point. So they'll usually ask you, solve for dy dx or solve for y prime. And how do you derive these? So it works a little differently. If you're someone who likes steps, here's the steps. So, and then I'll kind of demonstrate this. So the first thing, you want to differentiate both sides with respect to x. So the textbook that I've used says this right here, this y prime thing. Y prime is the hook-on factor for any term involving y. My way of saying this is when you differentiate, derive the y's, you also have to like chain rule y prime at the end. All right? None of your answers have been correct so far. Yes, you've seen that's not even a musical. Now, so you derive them, right? And then they say collect all the y prime terms on one side. So maybe you have a lot of y's that have been derived. So you have y primes. You want to put them all on one side of the equation. This is similar like when you have like a multi-step equation, you say solve for x. You get to a point, put all the x terms on one side, and then we factor out the x or do stuff like that. So we'll get all the y primes to one side. We want to factor out that y prime, trying to isolate it. And then usually we divide to solve for y prime. But really, all of this is isolate y prime, right? Or dy dx, whatever you want to call it. So we differentiate here. So really can think about it as two. Differentiate both sides, and then isolate the y prime. All right? And however you do this. Get a hint? No. So let's give you an example here. Let's take this one. Given this, find y prime. Pretty basic. Now, sometimes they say dy dx. All right, class. Did Borata last year? Did she write dy dx or did she write y primes? So so we might have done either way. So I don't care what you do. I like writing y primes because it's quicker. But in the case of this class, I'm going to write dy dx because it's easier to see if someone's like half paying attention to me. But typically I'd write y prime just it's faster. But the challenge could be if you're not paying attention, you could lose that prime part. Just like scribble really bad. Bad handwriting. Guilty right here. So first thing you do is you derive everything. So I'm like, d of dx, boom, derive it. For each term. The derivative of x squared is just 2x. Now, derivative of 2y cubed, well, that's power rule. So it'd be negative 6y squared. But like I said, whenever you derive a y, tag on a y prime, or I'm going to do dy dx in this, times this. Derivative of 3x is just 3. And then derivative of 6, this is where people forget. Derivative of 6 is just 0. That's a constant. Now, you might be asking, wait, why don't we tag on a dy dx at the end of the x's when we derive this? And this is kind of a sidebar here, folks. My answer is you do. But watch, it would be 2x. It wouldn't be dy dx, like dx is always in the bottom. It'd be dx dx since the variable is x. And those just cancel out. So you really are always doing this with x's, but because they cancel out, it's okay. Didn't know if you knew that. I know. So maybe it doesn't feel like a random rule. Wise. All right. So there you go with this. So my next step, I'll switch colors. I want to isolate the dy dx terms. It should be just this one. That means these two terms. Okay, I want to get these to the other side. Or I can get just this one to the other side. I don't care what you choose to do. I'm going to leave my dy dx over here. So I'm going to subtract 2x on both sides and subtract 3 on both sides. These cancel, 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 cancel. So I'm left with equals negative 2x minus 3 and negative 6y squared dy dx. Now, to isolate the dy dx, your next step would be just to divide by everything attached to it. And this whole thing. So these all cancel out. Left with dy dx. So yeah, you get that. And that's going to equal just this nonsense. Now, can you simplify this? Sure. You haven't answered it yet. Nope, haven't picked the movie yet. Now, can you simplify it? Sometimes you can. Actually, since everything is a negative, I can switch this to 2x plus 3 over 6y squared. If this was a multiple choice problem, sometimes you might have to do some rearranging or you'd have to do some canceling things out. A note here, as a common mistake, this is sidebar, but if I had this 2x plus 3 divided by 6y squared, some people might go, oh yeah, I know what I can cancel out. The 2 and the 6, and this turns to 3, this turns to 1. So it's x plus 3 over 3y squared. That's wrong. You kill kittens when you do this. You have to every term has to be canceled out the same. Can't just do this. This is bad. 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 Still no correct answers. All right, let's try another one. So building on this, there's a few different things we can do with this. Find the slope of the line's tangent. I'm not going to worry about normal. I hate normal. Normal is opposite reciprocal, right? Let's just do tangent and move on. Gross. Find the slope of the line's tangent. Okay, so the same thing as we do before at this point 3, 2. So that's my x1, y1. But now I have to find my slope. Your slope m is your dy dx at this point. So I got to find dy dx. All right. So let's do this. Derive everything. I don't care if you do this notation every time, but whatever. So that's 2x plus 8y times dy dx equals 0. People always forget. They just leave it as 25. Now, isolating this term right here. So what'll I do? I'll just subtract 2x from both sides. 8y. I wish I just see y prime so many less strokes of the pen. And then lastly, I will divide by 8y. You really, for this one, probably did want to isolate this first. And so I get my answer like there. Now, and if I wanted to, I could simplify it. But here's the thing. Okay, I'm going to simplify it just because. Negative x over 4y. At this point, since I've simplified it all the way, now I just plug in this value 3, 2. So dy dx at the point 3, 2. I'm just kind of putting this down here. I don't know how you do that notation correctly, but sure. That's going to be negative 3 over 4 times 2. So negative 3/8. So my slope of the lines, so I just had to find the slope, negative 3/8. Done. One hint for you guys for doing these types of problems, especially when you're plugging things in, is sometimes after I derive, you don't always have to isolate the dy dx first. Sometimes, especially if this is more complicated, I like at this point where I'm in red right here, I like actually just plugging in the numbers first because then I'm not dealing with variables. And to me, it's easier. So I'm going to demonstrate actually, instead of, I'm going to go off to this side. I'm going to go off over here. So what if I plugged in 3, 2 at this point? I would get 2 times 3 plus 8 times 2 times, let's say y prime equal to 0. So 6 plus 16y prime equals 0. Subtract 6 on both sides. And then, so negative 6. And then my y prime would be negative 6 over 16. Reduces to negative 3 over 8. So sometimes to me, it would be easier at this point to plug in. Since I'm just solving for dy dx anyways, giving a numerical value. You don't need to give the algebraic expression like this or this. I like plugging in at this point. All right? Either way would be fine. Unless they really want you to write this. So, just wanted to show both ways that it worked. And especially if this is more complicated, I would do it. You know, if you remember like partial, like you have to find the particular solution with integration. It's kind of like a implicit differentiation, like difficulty, but it's like the integration one where you have to you have to separate the dy's and dx's, integrate both sides, and solve for the c. I feel like if you ever have to solve for a certain value, do it right after the derivative or right after the integration. Makes the algebra easier. All right. My next thing. Okay. Let's just do another one. So dy dx and evaluate at this point. Okay, so this will be a little more challenging because we have this term right here. So when you have a term like this and you're deriving it, you have to, an x and y, you have to split it up and do product rule for just this. So watch. So derivative of this one is going to be 3x squared. And then, so this thing right here, especially when you got a negative, there's different ways people do this. I'm going to lump the negative 2x as one thing and the y as the other thing. So this is my f and this is my g. My f prime would be negative 2 and g prime would be 1 times, so y prime, derivative of y, or dy dx, whatever you want to call it. So my product rule is going to be, okay, so I'm going to say plus, and I'm just doing these in parentheses. Keeping track of negatives is weird. So my product rule, I go f prime g plus f g prime for my order. I'm going to go negative 2 times y plus negative 2x times dy dx. I don't know. I guess you didn't need parentheses, but I'm guys. Y dx equals 5. Derivative 5x. All right. So cleaning that up a little bit, 3x squared minus 2y minus 2x y dx plus 3y squared dy dx. Okay. None yet. So I want to isolate the dy dx terms at this point. That one and that one. So I'm going to subtract these two and add 2y. Oh, and didn't I say my rules? See, this is where it gets complicated. If I just, I have to find dy dx too. So I can't just do what I said before. 2x dy dx. How many steps do you really need to show if you were doing this on your own? So in APs, like, you probably should show this step right here, but like some of these, you know, if you don't show this work, all these little steps right here, that's okay, but you need to show this first derivative part. Like, you might do some stuff in your head. That's okay. And now I'm going to factor out the dy dx here, so they get factored out. So dy dx, negative 2x plus 3y squared equal to 5 minus 3x squared plus 2y. I would usually just go ditto. I would. And then the last step, you got to divide by this thing. I just do this. I don't want to write it again. dy dx is equal to 5 minus 3x squared plus 2y, or negative 2x plus 3y squared. That's so gross. Can you simplify it? Nah. Gross. Now, we do have to, and the problem is sometimes you forget. We have to evaluate it at this point. So to do this work, do that in a different color. Dark blue. The dy over dx at the point 1, 2 would be 5 minus 3 times 1 squared plus 2 times 2, negative 2 times 1 plus 3 times 2 squared. Now, if this is an AP test, that's my answer. I don't simplify. Don't have to. But let's do it anyway. 5 minus 3 plus 4, negative 2 plus 12. All right, so then I have on the top, on the bottom I have 10, top I have 2 plus 4 is 6, 6/10 or 3/5. There you go. All right, questions? Okay, I do have to do one of these. How many more of these do I have? Okay, last one. So what if you have to do double derivative and there is a difference here? When because I'm asking you to do it in terms of y and x. Usually they say in terms of y and x. And here's what happens. So, because I don't want my final answer to have any y primes in them. And you'll if you don't remember this trick, I'll show it to you. So let's do it like we've normally done. X squared plus y squared equals 3. We derive that. Get 2x plus 2y. I'm going to say y prime. I'm lazy now. Equals 0. So the first thing we want to do is we want to isolate that y prime, right? So I'm going to subtract 2x on both sides. Ways to even change colors. 2y, y prime, negative 2x. Divide by y on both sides. And my y prime is equal to negative 2x over 2y. You know what? I'm just going to say y prime equals negative x over y. That's the start right there. Now, I want to find y double prime, we derive this again. So if you derive a y prime, you get, oh, you can't see that. You get y double prime. And this thing is like a quotient rule. F and g. Your quotient is f prime times g minus f g prime, or g squared. In the case of this one, f prime would be negative 1. G prime would be y prime. All right, so I'm going to write it out that way. I'm going to go negative 1 times g, so y, minus negative x times y prime all over y squared. So you might say, oh, negative y plus xy prime over y squared. And you think you're right. But we want it in terms of y and x. That means this y prime is bad news. That means they don't want you. And this is that picky thing that AP does. I don't know why they care so much. But you have to plug something in for that. And what do you plug in? Well, you know what y prime equals. It equals this thing. So you just plug this in for this guy. So actually, my final answer, negative y plus x times negative x over y squared. Would I simplify that? No. Too much work. Super gross. They don't say to, and I'm not even going to try. I mean, you don't like fractions and fractions, but too much work. All right. That was it for those. Do more work if people request it, or maybe some more tomorrow. Need them. Inverse functions. So I'm going to explain this a little bit and show you some Khan Academy stuff. What is an inverse function and their derivatives? So if you have the textbook, you see this. Derivatives of inverse functions. I hate this. Like, I don't know what's going on here. Yeah, we only have 5 minutes. Do I pause this and do it next time? That's okay. I'm going to do it quick. Maybe we do it again. You know what? Maybe I just do this tomorrow. Let's do that. Tune in next time.